Well, welcome back. We're going to continue our discussions of calculus, and we'll introduce the standard integral notation, terminology, and draw a contrast between the definite and indefinite integrals. So, symbolic notation, which is commonly used for integration, consists of this elongated S. It usually indicates that what follows is to be integrated. So we have the integration of y prime dx is equal to y. We know that this quantity is the value y that we differentiate in order to get y prime. And we used several examples last time to illustrate this general process. Now, the term that we use to refer to this quantity being integrated is, we call it the integrand. So this is the integral of y prime dx, and this quantity inside that we're integrating is referred to as the integrand. And for the indefinite integral, we add in this constant c. So the integrand is the derivative of y. It's dy dx, or just y prime, whatever notation you like. And again, it's the indefinite integral. And we don't really know what this value of c is, but we know that there could have been a constant in there. When we differentiate whatever our guess is for y, whatever that actual y was, it could have included some constant value, and we'll show this graphically in a couple minutes. So in this equation up here, we have the integral of 2ax plus b with respect to x. We know that that's equal to the quadratic ax squared plus bx plus c. We know that this is an indefinite integral. We know that 2ax plus b is the derivative of some y. We've estimated what that is over here. And so this is our derivative. It's the integrand. The function we differentiate to get the integrand is the value y, in this case, in our notation. And c is just that constant of integration. It appears in the, it always appears in the indefinite integral. It doesn't have to be c. It could be, it could be q0, L1, something that makes sense within the context of the problem that you're dealing with. And in this, as we're just kind of developing these concepts in an abstract way, we're referring to it as c. So this integral, again, it's referred to as an indefinite integral, and it provides a general result for arbitrary reference values of c. And then the two flavors that we get the indefinite integral, we get the definite integral. And the definite integral is definite because it's integrated over specific limits. So in this case, we have 2ax dx is equal to ax squared plus c. In this case, we have the ax squared, but we're going to evaluate it at the limits x2 and x1. And that's what makes this a definite integral, because we have specific numbers. And we actually come up with a specific result here associated with the integral over a specified range x1 to x2. So as we go through this evaluation, the standard way of evaluating ax squared from x1 to x2, this integral, is to evaluate ax squared at x2. So we have ax2 squared minus ax1 squared at the lower limit. So it's the function evaluated at the upper limit minus its evaluation at the lower limit. And again, x1 and x2 are just the limits of integration. So, this function that we've shown before, if we have a function like y of x, the integrand is x, and we're asking that question, what is it that we differentiate in order to get the integrand? And that turns out to be x squared over 2 plus c, and this is just a triangle. The length of the base is equal to the length of the height, and it just turns out to be the area of a triangle. It would be a triangle with a 45 degree angle, and it would look like this. So we have the area of the triangle is equal to x squared over 2 plus c. Well, we really don't know what the limits are. So how big is this triangle? What is c? How far out does x go? So we have the area under a curve. That's what the result of integration in this case. We have x is just a straight line with a zero intercept, right? So we have y is equal to x, and it has a zero intercept. Could have a zero could have some other intercept. That would give us a different problem. But this is an indefinite integral, since we don't know what the limits of x are. So we just have x squared over 2. We know we have some area, but we don't know how far it goes. Now, if we express this as a definite integral, there would be some specified limits to the range of integration. And it would look like this, where we have the integral of x dx is equal to x squared over 2, evaluated at the limits x1 and x2. And we've said just by convention that we evaluate the result at the upper limit and subtract its evaluation at the lower limit. So let's take a look at that graphically and see what it is that we're getting when we do that. We've got these two values, x1 and x2. x1 in this case looks like it's going to be 0, but this is what we have. We have x2 squared divided by 2 minus x1 squared divided by 2. So we have a specific limit on the area in this case. We know this triangle doesn't go on forever. The x1 in this case is just equal to 0. So these would be two curves. Depending on what c is, we have y is equal to x squared over 2 plus c. So it could look like this. We could have c could be 0, and it would look like this. C could be something else. It would look like this, in this case 25. So this is the area for c equal 0, this curve. Just have c equal 0. And this is the area where c is equal to 25. It's still equal to the area, but we've added a 25 to it. We get this curve over here. Now, if we take a specific value of x, let's say 10, and our x1 is 0 in this case, then we know that the area is going to be 1/2 the base times the height. It's going to be 1/2 10 squared. It'll be 100 divided by 2, or 50. So that's for c equal 0. For c equal to 25, we add in this additional 25. So the result of our integration here is going to be 75. Okay, let's take another look at this process. So we've got this triangle. We're evaluating the function x from the limits a to b. We've got x squared over 2 evaluated from a to b. That gives us b squared over 2 minus a squared over 2. And that's the area of this. That's this area here from x equal a to x equal b. That's the area of the larger triangle minus the smaller one. And you're probably asking yourself, okay, well, what happened to the c? Well, okay, let's evaluate it. Let's be a little bit more detailed in our evaluation. We've got x squared over 2 plus c evaluated over the limits a to b. we evaluated at the upper limit, we get b squared over 2 plus c minus the evaluation at the lower limit, which gives us a squared over 2 minus c. Well, the c's cancel out. We end up with b squared over 2 minus a squared over 2. We don't have to worry about it. They cancel out. So let's take a look again at what we're doing with this definite integral. We're evaluating over the limits a to b. We get the result x squared over 2. We're going to evaluate it at a to b. This term, b squared over 2, is the area, we said this before, we said it's the area of the larger triangle. And then we are subtracting from that a squared over 2, which is the area of the smaller triangle here. So we get the area between these two values of x equal a and x equal b, of the function y equal x. Okay, so that gives you an idea, helps distinguish make a distinction between the definite and the indefinite integrals. Our indefinite integral is just the integral y prime dx. We get y of x plus some constant c. The definite integral, on the other hand, is y of x evaluated at the limits x1 and x2. And the next time we'll develop some basic integration rules. So we're going to come back and we're going to do more integrations and get a little bit more familiar with the process of actually determining what the integral is. So we'll see you next time.